After litter has been decomposed to the point where it's no longer recognizable, it becomes soil organic matter. And here we'll look at the decomposition of soil organic matter. So some of the most basic questions are, why does soil organic matter accumulate? Why isn't it decomposed at a rate that it doesn't accumulate and we don't really see much of it? Alternatively, why does soil organic matter not accumulate more? So we'll have a certain amount, that's a given, but why isn't there more of it? What are the constraints on the accumulation of soil organic matter in soils? Decomposition of soil organic matter is strongly influenced by its reactions with soil minerals. So one of the major things that's associated with soil organic matter in soils and why it's there has to do with its interaction with soil minerals. And essentially by this we mean clays. So clays that you find in soils are really important for the preservation of soil organic matter. The minerals associated with clays, clay minerals, reduce the decomposition rate of soil organic matter, thereby increasing soil organic content. Now when we talk about reasons why organic matter is not decomposed, we talked about biochemical recalcitrance, for example, and the biochemistry of those compounds that make it hard to decompose. So irregular structures, high bond strength, things that prevent enzymes from breaking it apart into smaller units. In addition to biochemical recalcitrance, we can have what's called physico-chemical recalcitrance. And unlike biochemical recalcitrance, it doesn't have to do with the biochemistry of the compounds and how hard they are to break up, but really physico-chemical interactions between the organic matter and minerals. And we call it here physico-chemical because it's somewhere in the boundary between physical interactions and chemical interactions. The most important part is to know that soil organic matter binds to clays, and that clay binding, so clays and soil organic matter bind to one another, and that clay binding makes that soil organic matter less accessible to enzymes. So when you have clays and soil organic matter that come together, enzymes have a much harder time accessing that organic matter and breaking it apart. So here's an example of the interface between a clay mineral and organic matter in the soil. And as we talked, if you have cation exchange capacity, that means your clays have a negative charge. And some of that negative charge is associated with cations. So you might have potassium that is attracted to that negative charge. But also, you can have organic matter that has charges with it, and often a positive charge. And so, for example, the protons on the end of this unit here have a slight positive charge to it, and it's attracted to the negative charge, just like potassium would be. So we can have here the H groups, or the OH groups, being attracted to clay minerals, and that's what's circled here. In addition, you can have minerals such as potassium that serve as a bridge between the negative aspects of soil organic matter. So when you have a slight negative charge around an oxygen, you can have a cation bridge, so potassium for example, that sits in the middle and bridges negative charges. So you have a negative charge in the clay mineral, a positive charge with your cation, and that's attracted to the slight negative charge on oxygens. So both through negative and positive charges in soil organic matter, you can either have a direct adsorption or some bridging associated with cations. So this schematic really shows the interactions between soil organic matter and clay particles. And it can be mediated by parts of the organic matter itself or water that's attracted to the soil organic matter also. So there's a whole host of ways that you can have attraction between clay minerals, be they have positive or negative charges, and soil organic matter. Now, in climates that are favorable for decomposition, substantial quantities of carbon can persist in mineral soils for thousands of years. So how is it that in places where decomposition happens really fast, you can have organic matter in soils that has been there for thousands of years? Well, part of this persistence has to do with a couple factors. One of those is selective preservation. So in litter, there's a whole range of compounds, and some of these are more biochemically recalcitrant than others. And the idea that some of those compounds can be selectively preserved is just the idea that all the labile material gets decomposed, and what's left over is the stuff that's the most biochemically recalcitrant, and that just takes a long time to decompose. But in addition, we also have transformation. And that transformation is taking relatively labile materials and turning them into more recalcitrant materials during enzymatic and non-enzymatic processes associated with decomposition. Now, essentially what happens during decomposition is that you create a soup. Enzymes and peroxides, for example, break down organic matter in soil into lower molecular weight compounds. And then, through other factors, these lower molecular weight compounds come together, react, and form recalcitrant structures. So we talk about humus production, and essentially that idea is that these labile compounds are reacting to form recalcitrant structures that weren't there initially in the litter itself. So we have preservation of stuff that was really recalcitrant, and we also have formation of recalcitrant materials too. Now, there's also polyphenols and quinones, other structures that are relatively recalcitrant. Some of these are present initially, others are formed. And when we talk about polyphenols, for example, these are compounds that have a group in here like this. You have a benzene ring that might have hydroxyl on the end. And these are super difficult to break apart. There's a lot of energy associated in this ring. And breaking this ring, in order to further break it down into metabolically active subunits, is very difficult to do. Quinones are byproducts that are similar to polyphenols, but all have this benzene ring. And these are super tough to break down. So if we want to sum up some of these factors that are associated with the production of soil organic matter and why it's recalcitrant, is that on one hand, we have labile compounds. And these labile compounds by themselves will never stick around for a long time, but they can be processed by microbial biomass and then turned into more recalcitrant structures. And that is a selective preservation, essentially. But you can also have things like lignin and waxes that are associated initially in the plant litter that are preserved selectively. And that's these pathways here. Now, after preservation, there's also transformation. And so labile compounds can get turned into more recalcitrant ones by microbial biomass, and that's microbial transformation. But also polyphenols and quinones can be formed through a whole host of reactions. So you start out with phenolics, for example, and then you can form polyphenols, and then those get turned in quinones, and this is really what makes up humus. So we have selective preservation of relatively recalcitrant stuff that's present or generated by microbes and then preserved. But then we also have microbial transformation that takes relatively labile stuff and turns it into more recalcitrant stuff. In addition, we've got formation through abiotic and biotic processes that generate polyphenols and quinones and these other things that you'll read about with abiotic condensation. So you start with plant litter. It has a whole bunch of different things. Some of these are selectively preserved, others are transformed into more recalcitrant stuff, and in the end, you get this class of soil organic matter that ends up being really recalcitrant biochemically.